All right. Hello. Welcome to day 2 of the 2022 REU Symposium. I'm Willow. I'll be your host this morning until lunch. Hello to everyone online. Please put in the chat if you cannot hear me or if any audio issues. Thank you in advance. So today, before we get started, just an announcement about tomorrow's poster session. Especially for everyone online. Tomorrow's poster session will begin at 9:30 a.m. and will be held till noon. Presenters, we will ask you to come at 9 a.m. to set up your posters. But feel free, please come join us and hear from these students more about their work from this summer outside of what they present today and even what they present today, along with having some snacks and some coffee that will be provided during the poster session. All right, today's session, all the morning talks are going to be are centered around the sun. I mean, this program is centered around the sun. We're centered around the sun, I guess, technically. Anyway, sorry. Comedian, I'll be here all week. Yeah, I haven't had enough coffee yet. Apologize in advance. So let's get started with Sarah. So Sarah, if you want to come up and we'll get you all mic'd up. Or hold the pack or set it here. Just if you set it here, remember to not run away with it.
Okay.
Okay, she should be on. Can you hear her?
Yeah,
Oh, thank you.
it might be useful.
You know, you're right. Yesterday, sometimes the space bar or the arrow key can't work. So if you just click on the slides,
Okay.
it should prove it.
Okay.
Say what I think this button.
Okay.
All right.
You okay? Sounds good. Alrighty. Hi, my name is Sarah Davis, and this summer I worked on preparing for the 2024 total solar eclipse with Citizen Kate, which stands for Continental America Telescopic Eclipse. I worked on this project through the Boulder Solar Alliance's REU program, and I worked with my mentors, Sarah Kovac, Amir Caspi, and Dan Seaton, all from Southwest Research Institute. Ever since Kate was founded in 2014, we've had 3 main goals: outreach, coronal research, and solar wind research. Eclipses are the perfect opportunity to teach people about the eclipse as people sometimes travel thousands of miles for these rare events. The Kate gives telescopes to citizen science teams along the path of the eclipse so they can take data for us. But of course, I'll explain more later. One of our big main research goals this upcoming eclipse, I guess, is coronal research, as we can see the inner corona best in visible light on the ground-based telescopes. So we're focused on studying connectivity in the middle to lower corona, and new polarizing equipment will help us map the distribution of free electrons in the corona. One of our other big research goals for this project is to study the solar wind, as solar wind flow is inhomogeneous, and single eclipse site observations last at best 7 minutes. Kate is unique in the fact that we will observe solar wind flow for the entire duration of the eclipse as it moves across America. And in doing so, we will be able to distinguish flow in different parts of the corona. So here is a close-up of the April 8th, 2024 eclipse path, starting in Mexico and going all the way up through Maine and Canada. We will have teams stationed along the path of the eclipse in the United States. And each team will take totality data as the shadow passes over them. As you can see, the path goes through many rural regions, such as indigenous reservations and farmland, as well as several major cities. This gives us a demographically diverse population to work with and a wide variety of communities to serve, including underrepresented communities, and give them opportunities in the STEM field. So here is a close-up of the sites along the path of the eclipse. Okay, and you probably noticed right away that these are weirdly shaped circles, and there's a lot of overlap between all of them. Okay, so these are the pictures. The circles represent the shape of the shadow as it passes over each site. So like each site is in the middle of the circle, and that's just the shape of the shadow. There's a lot of overlap between all of our sites. This just ensures that we get continuous coverage of totality as it passes through in case we have bad weather like clouds like today, or something goes wrong at a site with the equipment or anything like that. You can kind of think of it as an eclipse relay race. As totality ends at one site, it starts in another, with totality lasting about like 4 minutes at each site. We anticipate we will have 35 sites along the path of the eclipse, in addition to 5 floating sites. We're still trying to determine the location of all of the floating sites, but we know for sure we're going to have one down in San Antonio, Texas, at Southwest Research Institute there for media coverage and different outreach events. So 35 sites is a lot for one team to handle. So we are creating a hierarchy to have regional and state coordinators to help filter down communication and education materials. So we're going to have lead trainers as well. These lead trainers will all be undergraduate students, and they will help train our state coordinators and our teams. And as you probably saw from the path of the eclipse, it's a little funky as it goes through the Midwest. So some of our state coordinators are in charge of more than one state, but we believe they can handle it. So the 2024 project builds off of what Citizen Kate did in 2017. We're going to follow pretty much the exact same procedure. We're going to first test candidate setups and various equipment, train our citizen scientists, and distribute equipment to them. And then on the day of the eclipse, we will collect totality data. And then after the eclipse, we will analyze the data and compile it to make a 60-minute movie of the eclipse. And for the 2024 project, we are on the testing phase, which is kind of what I did and where I came in this summer. Alrighty, so the first big task that I had this summer was testing different hardware and different equipment. So the telescope you see here on the screen is a Daystar 80mm refracting telescope on an equatorial mount. That is the preliminary telescope I tested this summer. I also tested 2 cameras, a point gray grasshopper camera and a FLIR blackfly polarizing camera. We used the grasshopper camera to take data in 2017, and we anticipate we will use the blackfly camera to take polarizing data of the corona in 2024. So as you can tell here, I'm at my family's farm in this picture in northeastern Colorado. It's illustrated by the giant field in front of our house. It's perfect for nighttime observing, and I'll show you guys some cool pictures that I got here in a little bit. I also tested some additional hardware this summer, including a broadband diffuser and a polar alignment scope. So a broadband diffuser is legit just like a square piece of white translucent glass that you put in front of the telescope. This allows us to take better quality flat field images, which are used in the reduction process to account for variations in pixel, like if the pixels are dead or hot, whatever, it just helps make the image smoother. We commissioned a attachment accessory, as you can see, the one with the binder clips, from Craig DeForest. He made that for us, so thank you to Craig. It worked very well. I also tested a polar scope, a polar alignment scope, which helped polar align the equatorial mount. And here's a good visual for you. So what we want to do essentially is align the telescope rotation axis with the Earth's rotation axis. And I don't have a laser, but Polaris is like, of course, pointing towards the North Celestial Pole. So we essentially align it with Polaris. So you mount it to the telescope, go out at night, and try to get Polaris in this crosshair right here. And then you have your telescope polar aligned. This helps the telescope tracking motor work a lot better. and help us get like better quality data so the eclipse doesn't drift in our field of view. Okay, so some results that I got for the hardware. The telescope has anticipated field of view and focus quality and was great and for travel. Like it was small enough for travel, but still powerful enough for what we needed. But here are some pictures that I took this summer with the telescope. First is the sun, of course, with some really cool sunspots, and I just colored it using the DS9 application. The one on your right is the moon, obviously. So I thought that was a really cool picture. And then the one in the middle, this fuzzy blob right here, is the Andromeda Galaxy. So I thought it was pretty cool that I was able to see that with the smaller telescope and get a pretty good quality picture. The additional accessories that I tested this summer worked very well and will be a useful addition to improving the data quality that we take in 2024. So I also did some software characterization and testing. I used SpinView and FireCapture as two of my primary image capturing software, just through the computer, just some third-party applications. I use Python and IDL for all of my data reduction and image processing. And then I also tested a custom solar eclipse app made by people on the CATE project for previous eclipses to take totality data. So I just tested that application out and see how well it worked with this setup. One big thing that we wanted to do this summer was characterize camera performance so we could analyze the data that we got in 2017. As we hadn't really characterized our camera performance before, this was something that needed to be done before we actually looked at our 2017 data. So characterize the grasshopper camera, and to do that, we derived a photon transfer curve, okay, out of the flat field images that I took with this broadband diffuser. And yeah, so I took the flats using the broadband diffuser. It just makes the actual taking of the flats a lot easier. You just point the telescope at a bright light source and take a range of exposure times. You can also do it the old-fashioned way, like I did, just point the telescope at a white piece of cardboard. However, it's easier with the broadband diffuser. So I mentioned a photon transfer curve, didn't actually explain what it is. So while taking flats, you get pixel variations because CCD and CMOS cameras work via the photoelectric effect, and not every pixel works perfectly. So to account for this, we make a photon transfer curve just to see how our camera is performing and what our optimal range of photon counts or saturation is. So we take a bunch of flats ranging from 0 exposure to complete saturation. So every pixel you can think of like as a bucket. So every pixel would be full then. So one thing that we wanted to make sure was happening is that the average image signal was increasing with exposure time. So the longer you looked at something, the more photons you got, the more signal you got. And then once we got that, you plot the flat field image standard deviation versus the average image signal. So essentially you're plotting the noise versus the signal. And here is just an ideal photon transfer curve that I got off of ResearchGate, just to show you guys what the ideal photon transfer curve looks like. However, we ran into a lot of problems with this. When I was taking the flats, I found that the average image signal was decreasing with exposure time, which doesn't make any sense. Should be increasing because we're looking at things for longer, so we should be getting more photons, but we weren't. So we looked at everything. We checked the code, we checked the cameras, we checked the telescope, and eventually found it was issues with our software. So the software was writing out this weird contrast ratio with the pictures that we were taking and just totally like messing up our data and making it totally unusable. So that was a pain, trying to find that weird little setting to turn off the contrast ratio. Took a few days to find it, but we eventually got there, and we got our exposure times and our flats behaving like they should. So we increased in exposure time, our signal was increasing. So yay, we got the problem figured out. And then we plotted all of those flat field images for our photon transfer curve. So we plotted the mean signal and the noise together, and we got this curve right here. And we found that this camera is behaving actually really well. We found the optimal range for a camera is between 40 and 3,500 counts, which is about normal-ish for this type of camera. We wanted to make sure that the camera was following the ideal shot noise curve, which is kind of in purple there, if you can see it. That's just a statistical kind of model for how electronics in cameras should work. So we wanted to make sure it was following that, found our ideal range by following that line, and hooray, we got our camera characterized. Now that we knew how our Grasshopper camera was working, we could analyze data that we took in 2017. So this is the sequence of 8 exposures that our citizen scientists took during 2017 at Site 0, which was located in Western Idaho during the 2017 eclipse. To analyze this data, we wanted to create an HDR image. Okay, and what is an HDR image? It stands for high dynamic range image. It's an image that resembles what humans would see. They simultaneously capture the highlights and the shadows of an image. Okay, so like, for example, we want to see the whole structure of the corona. So we want to see like this inner part of the corona, but we also want to see this outer part, but we can't use this picture because the inner part is completely saturated. So we want to combine all these images in a way that we see the entire structure. And why do we need an HDR? Well, we want to see all of it. And the coronal brightness changes exponentially with distance out from the center and the lunar limb. So we need to figure out a way to highlight the structure and actually use this data. Oh, geez. We're good. Okay, to make an HDR image, I wrote a code that first normalized each raw image by its exposure time. So they were all on the same like base level. Then I took a look at all the pixels in all 8 images. If the value of that pixel was outside of our optimized range that we found from our photon transfer curve, so what was it, like 40 to like 3,500 counts, made sure like that it was inside that range. And if it wasn't, I marked that pixel as bad and didn't use it when computing the average of every single pixel across every single image. I then took the average value, I guess, for every single pixel and wrote out an image with that good data and got this. So hopefully you can see the structure of the corona is really predominant. And I just think it looks really cool, as you can see the inner corona very well, as well as structure in the outer corona. There's no saturation going on, which is awesome. That's what we wanted. So our goal with all of our 2017 data, which is about 2 minutes of totality at each site across like 70-ish sites. So that's a lot of data. We want to put it all together in like a 90-minute movie of the eclipse. So I think it's going to be fun. I also completed different outreach and education tasks this summer. I made updates to different procedures that we had, including stuff to do with the custom solar eclipse app that was created for this project, as well as different observing procedures that we have our citizen scientists follow. I also updated the procedure for the third-party application because that was a pain to fix and we don't want our citizen scientists running into the same issues. I also helped create curriculum and training modules for our workshop that we are going to hold for our regional coordinators and our trainers down in San Antonio, Texas in January of 2023. So this will be a good workshop to get to know the coordinators and just to teach them more about the project and get them familiar with the setup. And just kind of a fun fact, this is my mentor, Sarah Kovacs. She actually got her start too with this CAPE project. That's a picture of her down in Indonesia when they were doing stuff for the eclipse down there. Alrighty, so a lot of work to do before the 2024 eclipse. We need to keep preparing for the January 2023 workshop because that is coming up here pretty quickly. So we need to start ordering our telescopes and all of our setups and keep preparing for training modules and stuff like that. So we have a solid curriculum for all of our regional coordinators and our lead trainers to follow. We are then going to go down and observe the 2023 total solar eclipse in Australia with our regional coordinators and our lead trainers. This is just kind of like a practice run for them just to get more familiar with the setup and with the procedures so they can go around, like turn around and go teach everybody else. And then we are going to continue processing the 2017 CATE data, creating an HDR movie from all of the sites, and then of course recruit all of our citizen scientists that we will train for the eclipse in 2024. Alrighty, so that's all I have. I'd like to thank everybody here on the screen, including David, Sanjay, Jason, and Andre, and Craig for all the equipment and then the support. Thank you to everybody on the REU team and all of my mentors. It was a lot of fun. So any questions?
All right, thank you, Sarah. Any questions?
So what eclipses has Kate been part of, like that you brought telescopes to?
Yeah, so we've been a part of 4 eclipses so far. So I actually have pictures. So there's a picture of 2017 and then the crosshairs of 2024 there. And then we also did 2015 there, 2016 there, and 2019 there. So we've done 4 eclipses so far and hopefully more later.
I noticed a lot of eclipses do go over oceans, and it looked like you had some observations there. Are those on islands, or do you actually are there actually boats that do this as well?
So actually for one eclipse, I think it was the Indonesia one. We actually had teams on a boat. However, that data wasn't very good because the boat goes like this and can't have that in our eclipse data because a lot of drift. This is actually just from Javier Jubier's website, and I'm not sure why it has those little markings there, but I think that's just like pictures of the eclipse that other people took. But yeah, we found that observing on a boat really doesn't work. So we'll just try ground-based ones for now.
So kind of to ping off that question, I know they're ground-based stations, but do you think doing air stations would benefit in getting data?
In a way, yeah. I know my mentor, Amir, right there was head of a project that actually used airplanes to observe the eclipse. It would take a lot more training for citizen scientists to actually do that. So maybe that could just be its own separate project for now. And we'll see if we can get pilots on the team. That'd be kind of cool.
Any other questions? Any online? No. All right. Thank you, Sarah. Another round of applause. All right, so next we'll have Rachel. Rachel, if you want to come on up. I don't know why I can't move this. Okay, there we go. Okay, I'm gonna just either hold this or leave it here. Don't try and click it. It's a whole thing. It's a whole thing. Okay. And then based on some of the issues, so I would just click on the slides.
Click on
it.
All right. Hi, everyone. I'm Rachel Weir. This summer, I studied solar mosaics and how we use them to study the chromosphere with Dr. Kevin Reardon from the National Solar Observatory. So because this does study the chromosphere, first, I kind of just want to touch on what the chromosphere is.
So it is this middle pink layer that you see right here. It's about 2,000 kilometers across, and it's the middle layer of the sun. This is where filaments and prominences are formed. And in the chromosphere, the temperature can range from anywhere between 6,000 degrees Celsius all the way to 20,000 degrees Celsius. The density of the chromosphere is actually much like the Earth's atmosphere. So the closer you are to the center of the sun, the denser it's going to be. And the further out you get, the less dense it's going to get. And then the part that we are actually most interested in this project is that the magnetic field begins to dominate the sun's behavior in the chromosphere. So in this project, we're looking at the magnetic field and how it affects the sun and the chromosphere. So why did we choose to study the chromosphere, not another part of the sun? So like I mentioned in the previous slide, the magnetic field does begin to dominate here in the chromosphere. So to study it, we have to study the chromosphere. The chromosphere is also the site of a lot of activity as well. So there's a lot of changes in solar flares, prominences, filament eruptions, and the flow of material and post-flare loops can all be observed within just a matter of minutes in the chromosphere. And another big part is the conditions in the chromosphere are closer to the coronal conditions than they are in like the photosphere. So we choose to study it over the photosphere for this project because of that. There it goes. So why do we choose solar mosaics and not another way to study the chromosphere in the magnetic field? One of the main reasons is we need high resolution images to understand the physical processes that are occurring inside the sun. So with our detector, we have to have small pixel scales, sampling the images finely enough to sample the finest structures resolved by our telescope aperture. Sorry. But because the number of pixels of our scientific detectors is limited, it is extremely difficult to make one instrument that can take both wide field images and high resolution images. Not only is it really difficult, it's really expensive. So it tends to be easier just to take them on separate instruments and combine them later. So this process does give us a really good look at the magnetic field modeling that is taking place in the chromosphere. And it does so by showing us extreme crisp structures of the chromosphere and how they extend out. So like you can kind of start seeing it here. We'll zoom in later. But this is a mosaic done by citizen astronomers actually, but you can kind of start seeing the really crisp structures right in here. And then before I talk about my mosaic, I do just want to touch on the fact that we can use mosaics for anything that we want to study in high resolution. So all the way to, I guess, your left is a nebula mosaic. This was actually pieced together in Photoshop. That is kind of a difficult way to do it, but it does work. The middle is a solar eclipse, so it's the same process, laying high resolution images on a broadband. And then this is Jupiter's moon. Same thing. It was taken by, I think, a probe that went by, wish I could remember the year, but same thing. We just pieced it together. There we go. So how do we create a mosaic? So first we start by getting FITS images from the IBIS telescope. I'm going to be honest, I'm not going to try and read out how or what IBIS stands for because I will mispronounce every single word, and that will not be good for the presentation. So we get FITS images, which are these images right here. I did not do any filtering with those images. That is how I got them from IBIS. These images are, I believe, 1,000 by 1,000 pixels, and I have 196 of them for my mosaic. Other mosaics do have more or less, but that's how many I had to work with this summer. These images are then turned into these composite maps. So this right here, this is going to give us the coordinates we need to later on put it on a broadband image. So from this, we layer the composite images on top of that HMI continuum, which is just that full disk image. The continuum images are taken from SDO's helioseismic every time and magnetic field imager, which takes images 24 hours a day. And this is what we're going to lay the FITS images on. But unfortunately, because the continuum images are only taken every 45 seconds, it does take two other kind of images, so we can only get the images we want every 45 seconds. This causes a bit of misalignment with some of the FITS. So because the granulations are changing so quickly, we do have to realign them by hand, which is kind of annoying. But stuff like sunspots and solar activity, because they don't move as quickly, they are much easier to align, which I will show later. So I'm just going to show an example of how a mosaic is made. We don't do it. This is just a demonstration. This is not actually how we did it. We ran it through Python. Python made the mosaic, but this is kind of what it would look like if we could see the process. So it's just going to be laying these fits images over the broadband image and attempting to align them through the coordinates. And then we'll get through this really quick. And then towards the end, I do have an actual image of my mosaic. So, all right, so this is not the final mosaic. This is kind of a middle stage we have. So you can see that there's actually overlapping images here, and that's due to the fact that multiple images are taken of the same spot. And when we plot them over time, it's going to plot them on top of each other. So that's the same thing you can see with our sunspot right here. There's a lot of overlap there, and that's because towards the end of the exposure of this area of the sun, the telescope went back and took a lot of images of our sunspot just because it's the part that we were most interested in. And then we'll skip forward one more. So again, this is not the final mosaic either. Let's see. So here you can actually see at the edge, it is darker and closer to the center, it gets lighter. That is limb darkening. It's a process just caused by the photosphere, the different heights in the photosphere. It still does cause issues in the chromosphere, which is kind of annoying, but it does show you how the different heights and stuff that we are getting images from. And then this is part of the final mosaic. I quite literally did this yesterday. Yeah, so it's not finished. As you can see, you can probably tell if I can go back. This expands all the way to about 250 arc seconds, all the way to 960. This one stops right around 300, which is really unfortunate because that's right before that sunspot. But this is filtered through the H alpha spectral. So that's why we can see so much detail. The chromosphere does tend to emit high, or most clearly, I should say, in the H alpha. So that's why we tend to like to look at it. That's why you can see all of these. But so what do we actually do with these mosaics? Once the mosaic is made, what we're going to do is kind of go back a couple steps to where we had the FITS images with the granulation in the sunspot and not through the H alpha. And we're going to zoom in the part of the mosaics that we're most interested in. So normally solar activity, a sunspot of some sort. We have already done a rough alignment with the broadband image, but once we zoom into the images, we'll actually be able to align them much better. And then we will be looking at these through different spectral lines to get us to begin to see the magnetic field and how it moves around solar activity. So these are just the two images that I'm going to try to line up. Again, sunspots are just easy to line up because they don't move as quickly as granulations. So we're gonna. So you can see here, I zoomed in on that HMI image, and you can already tell there is a misalignment. So you can see at the top of this, there's a gap, and up here at top touches that top line. So what we're going to have to do is shift that new HMI image to match up with our FITS image, but I'll show you them stacked here in a second. So that's what it looks like when we stack that image over. It is kind of difficult to see with the colors, so I'm going to recolor it in a second, which will make it much easier to tell the difference in the misalignments. But you can kind of start to see it here where that dark sunspot and that dark spot in the continuum, they just don't match up perfectly. So yeah, here with the color, you can definitely see it a lot better. You can see that red spot, that is the sunspot on the continuum image. The FITS image, again, is that black spot. So they're zoomed in. So we're gonna have to align it. And honestly, I did it in probably the more difficult way. So I moved it by hand. I was shifting it, changing the header coordinates so they lined up. There is a way to cross-reference it with world coordinates. I didn't know how to do that. Somebody else probably does know how to do that, but I did it kind of the old-fashioned, crude way to get this image. So this is when they are lined up as perfectly as we can get. You can definitely see the sunspot fits almost perfectly. A lot of the granulation here does fit as well, but of course, granulation is changing so quickly. And because we have that 45-second gap between continuum images and not that much of a gap between our FITS images, we're gonna have just a little bit of misalignment. And there's honestly not a whole lot we can do about it. So where are we gonna go from here? So before that solar mosaic I was showing you with the H alpha, that is unfortunately as far as we got in the project. Probably had a couple more days, could have got that sunspot in, which is really what we want to look at. So in the next few images, I'm going to be using images from a paper by Kevin Reardon and Gianna Causi. So it just has a really, really nice sunspot. It'll be easier to explain how the magnetic field is bending around it than trying to make one up with mine. So what we're going to do is we're going to look at those images and we're going to use calcium 2, iron 1, and the H alpha to see into the chromosphere. So, excuse me, the chromosphere does emit radiation in all of these spectrals, but the one we are most interested in most of the time is H alpha. This is just due to the fact that the chromosphere shows very strong, highly concentrated structures when observing an H alpha. So that gives us one of the clearest views into the magnetic field in the chromosphere. So this is the broadband image from Kevin and Gianna's paper. It's exactly like my broadband images, just a different part of the sun at a different time and date. So there is that. And this is what it is filtered through that calcium 2. So you can start to see structures of the sun popping up. You can start to see lines, we call those fibrils. You can start seeing those pop up around the sunspot and in other places, but they are going to become much clearer when we look at the other filters. So again, this is iron 1. It's the same kind of thing. They're starting to show, but it is kind of hard to see it. So we'll just skip to the H alpha because it's definitely the most impressive. So here you can see the fibrils starting to bend around the sunspot. This is somewhat what my image would have looked like with our sunspot. You would see these fibrils bending around and moving away from it. We assume the fibrils are in line with the magnetic field. So they're kind of like the roads of the magnetic field. So that's how we assume that the magnetic field is moving around the sunspot, is based on these fibrils. And then I do just want to point out, you can still see fibrils whenever there's not solar activity going on. They're just not bending and moving as violently is not the word I'm looking for, but it's the one I'm going to use as it is around the sunspot. And then for this image, it turned out using calcium 2 was actually the best filter for it. So you can definitely see a ton of structure here. And I believe this was just filtered through a certain lens to get the color. If you want, this image is actually up at NSO. It is a beautiful image. I love this. I show it in anything I can. But yeah, you can definitely start to see the structures here. It is a lot clearer with the red background to see those fibrils and how they are bending around that sunspot. Right, so what are we going to be doing for future projects? Spectral comparisons is what is going to come next in this specific project. So what we are able to do is take alignment parameters derived by comparing our HMI full disk image continuum with the IBIS continuum image. The spectral line images can also be aligned directly, even though SDO does not offer the direct comparison, but because of the work we put in with the mosaic, we can now make those direct comparisons later on. And then DKIST, which is the new telescope from NSO, it is, I can't remember when it's about to launch, but it's going to have a higher resolution than IBIS does, but unfortunately, it's still going to have that small field of view. So it's going to have 4,000 by 4,000 pixel resolution. It's still going to have that extremely small field of view. So we're still going to have to do this mosaic process. Again, it's just so hard to get a full disk image with high resolution. It's just one of those things that probably isn't going to happen, which is really unfortunate. But so I think, honestly, the biggest conclusion to draw from this is that our research around the magnetic field our research shows that the magnetic field does tend to bend around sunspots and solar activity. You could definitely see in Kevin and Gianna's research, but again, in mine, you could see how those fibrils are moving. I think it's a safe assumption to say that it is moving around sunspots. I think that's pretty fair. And another big takeaway is just that high resolutions are really, really necessary for every part of astronomy and astrophysics, honestly. It's one of those things we do have to have just so we can actually study processes and stuff that we can't see with our broadband images. And then this is actually a mosaic, if it'll play. Oh, nope. I don't know if it's gonna play, it's just a YouTube video. If not, it's not that big of a deal. It's just a cool video. There it goes. Maybe.
No, okay. Sorry.
It's whatever. It's not a big deal.
Apologize.
It was just a video of how DCUS would be, their resolution is just a simulation of how a mosaic would be made with DCUS's images. So it's unfortunately you can see it because it's a beautiful video, but it is on YouTube if you look it up. So, but yeah, I just really want to thank Kevin for dealing with me this summer, dealing with all my questions. I know there was a lot, and definitely thank NSO and NSF for this opportunity. Thanks.
All right, any questions? I saw Bryce first and I'll bring it back.
So in some of the graphs, you had the picture of the sun. If you can go back, they're not exactly aligned up. They have like angled gaps at the bottom and side edges of your graph. Like you can keep going back. Like yeah, there's an example in one of them. Go forward to.
Sorry, this was like a.
Keep going.
I don't know if it'll. This one.
Keep going. Keep going. I think it's past this. Sorry about that. Oh yeah, example right here. Yeah, see there's a gap between in your image on the bottom, the side, and the top. It looks like it's rotated a little bit. Do you know the reason for that?
It's just how the images come. We do have to rotate them and fix the alignments a little. That's just unfortunately how we get the FITS images.
Okay, I see.
There.
So you were showing with a couple of the images that you had to hand align them. In that case, how many images were you having to hand align? Because at what point did you explore at all any way to automatically do that, or was it not worth it with the amount of images?
So it was really just this one image that I hand aligned just because we really wanted to see that sunspot. We had multiple images of the sunspot, but really just the one is the one I wanted to look at. So whenever you shift them, you like save the shifting in the code. So whenever you put a new image in, it'll shift the same. Most of the time that works out pretty well. So they're already shifted and aligned. Sometimes you do have to tweak it, but I didn't look into the cross-reference one. I probably should have, but honestly, I was pushing to try and get mosaics and stuff.
All right, any other questions? All right, let's give a round of applause to Rachel one more time. So we are gonna break a little early for our break. I was gonna say that's wrong. That means we are a little early to getting coffee. So, but once that is set up, you'll be up for grabbing that. And so for everyone online and in the room, we will start again at the top of the hour. So 11 a.m. Mountain Time. And Gabby will start us off in our next phase. So Gabby, if you can come in, like 5 minutes early, that would be great. Beautiful. Okay, thank you. Hello, welcome back. Thank you again for joining us for the second half of our morning session. We're going to start off with Gabby. If you want to come on over, I'll get you all mic'd. For people online, please let us know if there's any audio issues via the chat. Thank you. Is it upside down? And then you can either hold this or just leave it here. If you leave it here, it'll block off.
Okay.
And then with the slides, as you see the space bar sometimes does issues, I would just call it slide this you press or on this side.
Okay.
Yeah, cool. Whenever you're ready.
Okay. Hi, I'm Gabby. I'm from the Southern Illinois University in Edwardsville, and this summer I've been working with Phil and Vicky right here in the front row to determine Doppler velocities of solar flares using SDO-EVE data. So just a little bit about a solar flare first. Solar flares happen when there's magnetic reconnection, and this cartoon shows it, I can't reach, right there, right where that X is. And whenever there's magnetic reconnection, there's electrons that accelerate downward, and all their energy is put right into these areas, right in the transition region of the sun, and the plasma starts to heat up, and it gets so hot from all the energy being deposited by the electrons that it explodes. And there's some ions that get thrown down below into the surface of the sun and some up above the surface. So right here, the impulsive phase, that's whenever all the electrons are depositing their energy, and then the plasma builds up, it creates a loop. And then once that loop is made, that's the gradual phase. And then this graph over here on the left is the Milligan and Dennis paper graph. They used a flare to try and determine which ions get red shifted and blue shifted. So this 0 right here, this dotted line, is this region right here in the transition area where the ions get pushed up or down. So these ions down here, all of these ions that are below that line get pushed down to the surface of the sun, and all the ions above get pushed up to into the atmosphere of the sun. So we're trying to see if we can recreate this graph and get similar results to Milligan and Dennis, but we're going to be using our SDO-EVE data. And EVE is on board the SDO satellite. SDO has 3 other instruments on it, and it launched in 2010. EVE measures soft X-ray light and extreme UV light. And for this summer, I've just been using MEGS-A, which is one of the spectrographs on EVE. So MEGS-A is right there. And MEGS-A measures a 5 to 37 nanometer range of light. So this is what the data from MEGS-A looks like. So this is how it just comes in. It comes in pixels, which is important because we'll be converting those pixels into wavelengths. But here you can see I have a picture of the sun, and you can kind of see how it lines up with those spectral lines on the image. So EVE just takes an image of the whole sun. So on this image, the left is a 37 nanometer range of light, and to the right, it's 5 nanometer range of light. And each of these spectral lines belongs to an ion. So for example, this really bright spot right there, that's helium-2 3O4. And this is what it looks like during a flare. So the one before, so let me go back really quick. This is before the flare. And this is what the data looks like during a flare. And this just kind of shows even more where these lines belong to on the sun. So this flare right here, it's sort of towards the center of the sun. So these spectral lines that show up here that weren't there before, those are just from the flare. That's why they're sort of towards that center of these 2 slits here. So our goal again is to take that data from Eve, and we're going to try and create a wavelength scale. So converting pixels to wavelengths and measuring the Doppler shifts of the ions and trying to find their velocities. And we're going to try and get better spectral resolution than the current wavelength scale that's been used. So currently, the wavelength scale is made by using collapsed data and by taking a vertical average of the data. So each row, so right there, this is all pixels. And then there's rows of pixels, and all those rows, let me zoom it in a little. So this is just looking at bottom portion. So I'm gonna go back really quick, just to explain that. So this is MEGS A1 on top, because there's two slits on MEGS A, the top and the bottom. So just looking at MEGS A2, because that's all I've been using to take the data for the summer. So there's rows for every pixel. And for every pixel, how it was currently being done to make the wavelength scale, you take the peak locations of every single emission line, and you take their locations and collapse the data and average the data based on where each peak location is on each row. But there's an issue with that, and I'll explain that right now. So if you look at these, the longer lines here, these are all ions present just in the sun. And I put a vertical line here to kind of show that they are mostly pretty vertical, and later I'll show that they're actually not perfectly vertical. But this shorter line here, this belongs just to a flare emission line. And you can kind of see that it's tilted. And I just extended that here. You can really tell that it's tilted now. So if we were just to collapse this data and take the average of the data, if we look at the row above, it's more to the left. And if we look at a row down here, that emission line is more to the right. So our emission line might only be so thick, but whenever we collapse that data and take those two averages that are more to the left, more to the right, it broadens that spectrum and we lose resolution from that. So we're trying to find a better way to, or a way to find better resolution. And this graph shows that even more. So that black line is just the pre-flare, so just during the sun. And you can see that it's still not perfectly straight. Like down here, it starts to go up, and every point here is the peak location according to the row number. So you can see it does kind of deviate, go up and down. But the impulsive and the gradual phase, which is during a flare, you can see that's really slanted, and that shouldn't be happening. And we think that's due to an instrumental effect, due to the fact that the flare is acting like a point source. So really, ideally, what we would want to see is these red and blue lines coming from the flare. They would have the same slope as this pre-flare line, but they would just be shifted up and down depending during the phase of the flare. So the first thing we have to do is try and correct for the pre-flare line. So we need to try and make the scale so it fixes how it deviates up and down. And then the fact that the flare is tilted, that's an issue that we came across later. So first, just looking at the pre-flare data, how are we going to fix that emission or those emission lines to try and get a better spectral resolution? So again, here is just a pre-flare image. We used a flare on February 15th. Again, this is MEGS A1, MEGS A2 down here. I'm only using MEGS A2 data, so we're just going to focus on that. And these background, I don't know if you can really see them on the screen, but these white dots in the background, that's all background noise, either due to the instrument or particle hits. So I took a 12 image median to get rid of the noise. So now it's pretty clean. This spot right here, it shows up more during a flare, but this spot here, that's just the SAMS camera. There's a camera on Eve, and that's just where it's at on Eve. So this has nothing to do with our data. This is separate. So then just looking at MEGS A2, now if we take just a single row of data here, this is what it looks like. The graph here is what that single row looks like. So I kind of have them lined up here. So this is like helium-2. So here's helium-2, 3, 4 again. Here's some iron lines, and then they all line up. And what I did, I isolated 11 different ions. So for just this example, this is iron 11. So I take that ion and I just isolate it. So it looks a little bit like this. And then I Gaussian fit it to try to find its exact peak location. So I did that for 11 different ions. And that's just my table that shows all that stuff. So all the ions, their peak locations, and their wavelengths using the Chianti database. And I created this fit. And this is a third order fit. And it's a third order fit, not linear, because there's a curved grading on the detector, and the detector is flat. So that's why we need a third order fit. We can't just use a linear fit. And so this is our wavelength scale, and this is just for that one single row of MEGS-A2 data. So now that I have one row, I have to do that for all the rows of MEGS-A2. So this plot is just showing 6 out of the 11 ions that I fit, and they're just centered around their medians. That's why they're all close to each other. But you can see their peak locations from their median, and then the x-axis is the row number. And for our flare, we only used rows 290 to 350, and there's another graph that shows why we did that. This is just what they all look like, and we just took the median to kind of see if they had a similar pattern and to check how good the fits were. So if there was one line that looked super crazy and out of place, then I knew there was something wrong with the fits and I needed to go back and fix it. So this is, again, looking at just one row of data, because I created this plot for every single row of MEGS-A2 data. So that was from row 0 to 512. So this is just pointing out one single row. And again, similar to the other plot, we used a third order fit. The blue line is just a linear line, just to show that it really isn't a linear fit. So we do need to use a higher order. And the red points are just showing the different ions. So for example, this third point here, this is helium 2304. And we did a little bit of math to find out that from that peak location to the scale, or to the fit, it deviates about 20 kilometers per second. So now that we have our scale, we can start applying that to our flares and try and measure their Doppler shifts. I don't know if I said that right. I'm gonna say that again. We got, oh yeah, I did say it. We have our scale, now we're gonna apply it to our flares. So now that we're looking at the pre-flare on top and the flare on the bottom, you can see again that there's some lines that only show up during a flare, but we're also focused on the lines that show up in both, right? Because we made the scale for the pre-flare. So for example, this helium-2 304 again, during the flare, it's gonna shift maybe to the left or to the right, and that's what we're trying to measure. So that's why we made the scale for pre-flare. Now we apply it to flare to try and see how much it shifted by. So this is during the impulsive phase. So this is like during the first slide where I showed that this where all the electrons are depositing their energy. That's this. And now the gradual phase has more lines that spectral lines that show up. So now that we have those two, we have to subtract the phase or the pre-flare image from the phase. So we get left with just the flare or just the spectral lines. So this is what that looks like. And then I have axes on these just to show again how the flare is only present during rows about 250 or 290 to 350. So that's what this shows. And then again, we're just looking at MEGS-A2 data. And again, I just highlighted, here's the flare and then kind of where its location is on the EVE data. So once we found their shifts, we calculated their velocities. So on the right is our plot compared to Milligan and Dennis's plot here on the left. And as you can see, it looks very different. So everything over here on the right, yes, that's right. It's, we think that this is just mostly noise, because these ions that we use to make the wavelength scale during the impulsive phase, they're not really present. So whenever we look at, when we subtract that pre-flare from that flaring image, there's really nothing there. So we think this is just mostly noise, and there's really not enough good data to accurately map out where they would be at. But helium-2, there's two different ions. There's helium-2 304 and 256, and they're overlapping each other. That's why you can only really see one, but there are two there. And if you compare this to the Milligan and Dennis papers, you can see that they are in different spots. So we're saying that we got ours to be blue shifted, and they're saying that they got theirs to be red shifted. And we also suspect that there's something wrong with this because just physically the expectation is that it would be red shifted. So we knew that there might be some sort of error that we encountered. And that error is that the flaring lines are tilted. So this is something that we found out later after we plotted the stuff, and we we're like, wait, there's something really wrong. This isn't right. So we looked closer, and that's when we made this graph, and we noticed that there's clearly a tilt here. So once you get lower in row number, so kind of comparing this picture up here, you get a higher, or you get a bigger difference from the pre-flare to the flaring emission line. And then once you get closer, they start to get, once you get higher in row number, they start to get closer. And again, we're just plotting here rows 290 to 350 because that's where our flare is present. So I could have extended these lines, but once we got to other row numbers, it would just get really noisy because there's nothing there. So again, this just shows that there's some sort of instrumental error. And here's another graph that shows that again. So this black line is the pre-flare emission line for helium-2 304. And I have them color coded from rows 290 to 350 just to show how much they shift. So just looking at the peaks of each one, the pre-flare starts kind of towards the middle of the graph. Then it goes over to the left to a shorter wavelength, and then it shifts over to the right to a longer wavelength. And that just shows us how the lines are tilted. But making this graph also showed us that the flaring emission lines are actually not as broad as the pre-flare. I forgot the opposite word, but so the pre-flare is broader than the flaring is narrower. That's the word. So this actually is good news because we know that this gives us better resolution. So having these narrower lines means that it'll be easier for us to isolate peaks. So in some ions, we had maybe like double peaks. So they were kind of hard to differentiate between two or where the exact peak locations were for each ion. So having those narrower lines during the flare just means it makes it easier for us to find those peak locations. So this means that we can now use a time after the gradual phase peak, so during the flare still, to create a new wavelength, because we do have that slant to the flare line. So we can't use the pre-flare line because that's for straight, mostly straight, and then the other lines are slanted. So we can't really compare the straight to the slanted. So we're gonna make an EOS wavelength scale to use the time during a flare. So we're comparing slanted line versus another slanted line and another slanted line. And after we do that, we're gonna try and find the top blur velocities again and recreate that Milligan and Dennis plot. And eventually this could get expanded to MEGS-A1. So if you can see kind of in the background, I have that spectral image again. So we only used MEGS-A2. We can expand that to MEGS-A1, and we can even analyze other flares using the same method. But this would be something for the future, not right now, because we ran out of time. And I know Phil is very upset about that, but I'm upset about it too. But this is just something that we could do in the future. So even though we didn't get some like the results that we wanted to see, we found out some other cool stuff. So now we can even make our wavelength scale even better. So just a quick summary of what we did. We try to make a wavelength scale for the pre-flare to correct for that deviation in peak locations versus the row number. And then we found out that these emission lines were tilted due to some sort of instrumental effect. But we did prove that we can get higher resolution using flaring data. And all of this just kind of shows that there's some really good potential for new flare studies because we can get higher spectral resolution using the new data. Yeah, so thank you, Phil and Vicky, for being the best mentors ever and for teaching me so much. And I had a lot of fun. So thank you. And thank you, Wendy and Claire and Willow and James. And that's it.
All right, thanks, Gabby. Any questions? Any questions online? All right, well, I have a question. So you talked a little bit about sort of what you would do if you had more time. So if you had like a whole nother 10 weeks, how what more would you do, maybe outside even the scope you just talked about?
There will Eve, kind of how I was showing before, Eve has different types of spectrographs. So if we get to analyze all of MEGS A1, there's MEGS B, which kind of gives us also an image of the sun, but completely different. So I would guess I would try to make a wavelength scale for that and try and compare the two, see how one really does give you better data than the other, how they compare.
Awesome. All right, any other questions? All right, round of applause for Gabby. Oh, that's cute. I don't know where the green. Had a green. It's meant for mice, but that's okay. The camera's cheaper. I want to make sure it's shared. You're gonna click the arrows because you're on. Okay.
Hi. Hello, everyone. My name is Mackenzie Baird. I attend Villanova University, and I have been doing work this summer with Dr. Shashant Tripathi and Dr. Kiran Jain from the National Solar Observatory, and our project has been acoustic mode frequencies and surface activity over multiple solar cycles. So a brief introduction, this project deals with helioseismology, and some of you might be wondering, what is that? What is this fancy word? And essentially, helioseismology is the study of sound waves throughout the sun. So this image over here on your all's left, this shows propagations of sound wave moving through the center of the sun. And particularly what we're curious about is these high degree acoustic modes, so these ones that are propagating closer to the surface of the sun. And what we're going to be tracking and looking at is how the surface of the sun oscillates with respect to these sound waves. And particularly, we track this using Doppler diagrams that show things moving in and out. And one thing that has been known is that these frequency shifts are proportional to the surface magnetic field distribution. And so that is something that we are going to look into, as well as the temporal and latitudinal variation of these shifts. Big ideas here is to improve our understanding of the connection between what's happening inside the sun and what we can see happening in the solar atmosphere. So we're going to be essentially looking at these frequency shifts as an activity proxy for other things that we see on the atmosphere of the sun, but connecting it to what's happening inside the sound waves. And specifically, we're looking at the end of solar cycle 23, all of solar cycle 24, and the beginning of solar cycle 25. And one of our goals here is to try and visualize the solar dynamo, which is believed to be generated within the Tahoe line, which is within the sun. And so by directly looking at these sound waves which are moving throughout the sun, we hope to better understand that generation of the solar dynamo. So brief overview of the data source we're using. We are using data from GONG, which is the Global Oscillation Network Group. And GONG has 6 sites across the Earth, as we can see here. And the importance of GONG observations is that we get continuous observations of the sun as best as we possibly can. It is a ground-based telescope, so it's subject to weather conditions and instrumental issues. But the main goal is that when we can't observe the sun in one place, hopefully the other sites pick up observations. And specifically, we are dealing with more local helioseismology, meaning that we're looking at specific areas of the sun. So our data that we look at is broken up into tiles, like shown here. We see that the surface of the sun is broken up into specifically 189 tiles that are each 15 degrees by 15 degrees. And they go from 52.5 degrees south to 52.5 degrees north in latitude. So we're looking at the area where most magnetic activity happens, or where we see most sunspots. And one thing to note is that this data is passed through a thing called the ring diagram method. And essentially what this does is it maps the power after the data has been taken from its time space domain and put into its frequency domain. So if you bisect the individual frequencies as shown here, we get this ring formation. And these rings essentially represent areas of high power. And if we were to take a slice along this, which is what we do for Kx and Ky, we find an angular degree L. And if we take the slice, we look at the frequencies at each of these power modes and find the spherical harmonics N. So here we have N from 0 through 6, 1, 2, 3, 4, 5, 6, 7. Oh wait, well, 6, sorry. Okay. And yeah, one thing to note too is that in total, we're looking at 20 years worth of data, which means around 1.2 million tiles roughly are analyzed. Data characteristics. Also, it's important to know that we have less data for cycles 23 and 25 than we do for cycle 24. So we're looking specifically at the last 7 years of cycle 23 and just the first 2 years of cycle 25. And so if our data has 100% duty cycle, essentially this means that for each of the 1664 minutes that the tiles are tracked, we have an image for each minute. So this doesn't often happen. As we can see, we don't have any data at 100. And data that has less than 70% fill, we disregard. Some other data sources that we are using is magnetograms, also taken from GONG. This is an example here. And the magnetograms are tracked in the same way that our frequency data is tracked, in such that we have 189 tiles. And so we can correlate the magnetic activity at each of those tiles easily with the tiles that we're looking at in terms of the sound waves and the oscillations of them. We're also looking at the international sunspot number, which I've plotted here for, this is a long time range. We're not looking at that whole time range, just from the years I already specified, 2001 to 2021. And we're also going to be looking at the 10.7 centimeter radial flux, which is another activity source that helps identify magnetic activity. And to do all this, here's a little image of the solar dynamo again for reference of what we're kind of trying to probe and understand better. So in order to calculate how these frequencies change over time, we use 2 different equations. And the first equation we look at is the specific spatial shifts. So these are looking at individual tiles and how individual tiles differ from the daily mean. And then the other equation we look at is the global shifts. So looking at how the shifts over all 189 tiles summed together change with respect to a period of solar minima. So after doing this first equation, we're returned a plot like this, where we find the correlation coefficients of the magnetic activity at each individual tile with respect to the frequency shifts we see at those tiles. And because we have the same sort of breaking up of the tiles for MAI and frequency shifts, it's easy for us to just align those tiles by latitude and longitude and find the correlation. And one thing we note here is that there's really high correlation at periods of solar maxima. But then we get to solar minima, we get anti-correlation almost. So we get these vast dips in our correlation. And so we look at this further and break it down into the specific MAI values and what correlation coefficients we find for those magnetic activity indices. And essentially what we see here is that when we have low magnetic activity, we have very little correlation, and the correlation goes all the way from negative 0.4 up to 0.8. But then when we have higher magnetic activity, the correlation remains around 1 or close to 1. And here it's important to note, we're just looking at the second half of solar cycle 23. So it's easier to see these little partitions of each year, where it's easier, you can see the progression of the magnetic activity as it increases throughout the solar cycle. And here, because we were starting at maxima and going to minima, we see the earlier years have higher correlation and later years have smaller correlation. But for solar cycle 24, we're looking at everything. So since the cycle goes up and then down, the mapping is mapped on top of itself. So it's not as clear to see individual years. And then when we do the global shifts, we took a period of solar minima, which we found to be in December 2019. And we found this from taking the rolling mean of the magnetic activity index and finding the minimum point, which existed in December 19th, 2019. So we took a period of exactly 12 days. Specifically, this was from December 17th to December 31st, and found the mean of each individual mode or specific frequency, specific modes that we're looking at, and finding the mean of their frequencies, and then use that as a reference frequency to see how at each individual mode with respect to time, those frequencies change. In other words, we're looking at the temporal variation, and we find this pattern here, which we also compare to the magnetic activity index, the international sunspot number, and the radio flux. And these are in normalized units, so that way it's easier to see the trends and how they are similar. This is done mainly because sunspot numbers can have values up to like 300, whereas magnetic activity just up to 10. So it just makes it easier for seeing. And we can tell clearly that they are all very similar or follow the same trend generally. So we look at this a little bit further, and we break up the signal into its individual solar cycles. So here we have solar cycle 23, this is solar cycle 24, and this is solar cycle 25. And we find the correlation between each of these data sources and find that they all have values around 0.9, or a lot of these are very high, 0.99. Basically what this tells us is that what we're looking at is very strongly related and strongly correlated. So then we, because we just found that it was linearly correlated, let's plot those linear correlations. And when we do that, we get what we see here. Here in blue is cycle 23, green is cycle 24, and red is cycle 25. And these numbers that I have put here are the slopes of these linear lines or linear fits. The black line is for total for all solar cycles, our total 20-year data range. And one thing that we note that's interesting is that these slopes are not the same for each solar cycle. So there's differences depending on what point in time we're looking at. And specifically solar cycle 23 tended to have the steepest slope with the magnetic activity index. And essentially what this means is that it takes less magnetic activity for there to be frequency shifts for solar cycle 23. Of course, we only have the last bit of solar cycle 23. So it'd be interesting to see how this slope changes if we had the whole cycle, and if it would perhaps maybe look more like cycle 24. We also split up our observations into individual hemispheres and look at the spatial variation on the sun. Here is the northern hemisphere, and down here is the southern hemisphere. And one thing we know is that they don't look the same. So the frequency shifts actually tend to peak earlier for the northern hemisphere and later for the southern hemisphere. And when we look at the total, this one in purple, I just realized red and blue makes purple, and I didn't even think of that. But the northern hemisphere, we can attribute this earlier peak to, whereas the later peak is more attributed to the southern hemisphere. Another thing to note too is that these frequency shift values for the southern hemisphere go up to 3, whereas for the northern hemisphere, it just goes up to 2.5. So we can overall conclude that the southern hemisphere is stronger in this case. And then we split it up even further into individual latitudes. And here we're looking at 15 degrees north and south at the top and 30 degrees north and south at the bottom. And I've plotted in purple and green the magnetic activity, and in red and blue the frequency shifts. And one thing we notice is that these are not, the way that they are correlated is different for each latitude. Specifically for 15 degrees north, we see that the magnetic activity in the northern hemisphere doesn't quite match the shifts. The purple peak occurs before the red peak does, although these green and blue peaks are very similar. And then when we go to 30 degrees, we see more similar patterns here. So this is just clarifying that there's more going on when we break it down and look at individual latitudes. And we find that the global approximation misses some of these little differences. Next thing we did is applied the wavelet transform. And this is something that I'm really curious about and did in a previous project. So I thought would be cool to apply to this project. And me and my mentors talked about it and thought it'd be a cool thing to do. And so essentially what the wavelet transform does is it's similar to the Fourier transform, but instead of taking a signal and fitting it to a sine curve, we're fitting it to this individual wavelet. And specifically, this is the Morlet wavelet, and this is what I used for my transforms, but there are several different types of wavelets which can be used. The reason I use this wavelet is because it best fit the signal when you looked at smaller time stamps. But the big importance thing about wavelet transform is that when we pass something through the wavelet transform, we have strong time and frequency resolution. Whereas if you do the Fourier transform, you just get frequency resolution, and it doesn't tell you what point in times those frequencies are apparent. But essentially what happens is the signals fit to the mother wavelet, which has been translated and dilated to create a bunch of daughter wavelets. And those translation and dilations are kept track of by the computer. And then we're returned a power spectrum, which essentially looks at the periodicity of the signal. This is supposed to be down here, but this period here is years. And this y-axis is the same as here. So we're looking at time on the y-axis and periodicity on the x-axis. And one thing to note about this diagram here is that sections in yellow signify more power, whereas sections in black are less power. And specifically, sections which are circled in black are significant. We kind of disregard this down here, though, these smaller periodicities, because they're likely due to just the amount of time that the data is taken and perhaps noise. Also, same with up here. Here I did the transform with just the sunspot data from 1920 to 2020, and we find that the only significant period other than these noisy periods, which we can disregard, is the 11-year solar cycle. So this is sort of a proof that we're finding what we want to find and that it's working. And then we do the same thing with each individual latitude. So this animation here is just going through each individual latitude and the returned power spectra I got for each one. Also at the top here is the reconstructed signal. So the important thing when doing this was to make sure that the signal we pass into the transform, we get something that looks the same when we actually reconstruct it by the transform, what it gives back to us. And one thing to note here is that we see the 11-year periodicity, or the strong band that we believe is due to the 11-year solar cycle between 8 and 16 years. And then there's these periods of 2 to 4 year periodicity that happen at different points in time at different latitudes. Specifically, at some latitudes, it's at 2010, and at others, it's around 2012. And this is something we're looking further into and could possibly be due to a quasi-biennial period that has been neither confirmed nor denied. This is something that we're curious about. Also, there is 1 year periodicity that is noticed at some places, and this is inherent to our data since the angle in which the sun is tilted with respect to the Earth's ecliptic and everything changes throughout the whole year from negative 7.23 degrees to positive 7.23 degrees. So because of that, that change is inherent in a lot of our signals. And so some of those are being picked up. All right, so main takeaways. Basically, it's important to note that asymmetry exists on the sun and with the surface magnetic distribution. From these high correlations we found, we can say that what's happening with these sound waves inside the sun is correlated or affected in some way by the magnetic activity. And the global observations of the sun also tend to gloss over little details in each individual latitude that show differences. Also, we have found possible evidence for a quasi-biennial period. This is something we're going to look further into. And solar cycle 24 tended to have weaker activity in the northern hemisphere, while the southern hemisphere had stronger activity, or at least stronger peaks in frequency change. And solar cycle 25 already is on track to be strongly correlated with the magnetic activity index, basically showing that we can keep looking at these frequency shifts as a way to sort of understand the surface magnetic distribution. And that's all. I'd like to thank my mentors and the BSA and National Solar Observatory and NSF for the grant and everything. So thank you.
All right, any questions? See a hand.
Hi, so my question is, network groups like Gong are really sufficient in studying space. Do you think adding more observatories to this network group would help, and in what ways would it help and enhance learning?
I think there definitely could be benefits to adding more sites. I think that Gong is a well-established network group and has been for a while. And I think that, now you can have in-space satellites, and part of the reason why we don't use the data from those is because they take really good high-resolution data, but only for certain periods of time when the instrument is in front of the sun. So perhaps there could be maybe better resolution gained from adding more networks. I think that the distribution, though, right now tends to catch most 24-hour signals, like look continuously at the sun. So.
Okay, my name is Kiran, and Mackenzie was working with us, with me and Sushanta. So I would like to say, like, adding more observatories to the Gong network will not improve the duty cycle. We have done this work and we have found 6 is the reasonable number of sites, and that will give you the maximum duty cycle.
Okay, any other
Awesome,
questions?
thank you.
I'm so confused.
On the screen, you have these 6 observatories. They're located on the Earth, correct?
Yeah.
Okay. How do you guys make sure you're correcting for like the position of these different observatories? I feel like you might get a slightly different angle if you have like an observatory in the northern hemisphere versus the southern.
Yeah, that's something I don't know too much about because I just was given the data and then dealt with it, and I wasn't part of the process of detrending data for those type of instrumental corrections. I know that there's definitely a process that it goes through because we have overlapping, and especially the tiles that we're looking at overlap. So there has to be calibration done for that to make sure everything lines up. But I don't know the specifics. You can ask one of my mentors, probably would know better. So, yeah.
Sometimes we also use like you do HMI, just test for instrument, that's what. So we also go get in HMI to make sure that all of it. But still, it cannot be 100% correct. There is some.
Yeah, I mean, that's what I said. We use HMI data most of the time to make a cross correlation with our angles and make it 100% sure, but it cannot be 100% correct. So there is still some differences in the P angle, which you can see in that's what you see the annual periodicity 1 year.
Yeah.
So we try our best.
Yeah.
And I would like to say, like, we have our independent method. We really don't use HMI. We just cross check, but we have our own method to correct position angles. Yeah, and we cross check with HMI how different these are.
Awesome, thank you. All right, we have one more question over here.
Nice job, Mackenzie. So I have a question for you about the slopes of your frequency shifts. And you were talking about the fact that you had different parts of the different solar cycles. I was wondering if there might be any benefit to this method in trying to figure out what part of the solar cycle we're in. You know, could you say that if you have cycle 23 has a slope that is greater than cycle 24 versus 25, that if you, the beginning of one solar cycle, the end of another, is there anything in there that could end up being useful from a prediction standpoint?
Yeah, actually, I mean, that was part of the, can you guys hear me? Or, okay, the point I was trying to make was, since we only have the end of cycle 23, this steep slope could be characteristic to just the end of that cycle, or it could be characteristic to the whole cycle. That's something we can't quite conclude right now. But if we did look at just smaller periods of time, it would be interesting to see how the frequency shifts are either steeper slopes or have less steep slopes at different points of time in the cycle, and in what ways is like cycle 24 right now, because we have the whole cycle being like generalized for different behavior happening at different points in time.
Thank you.
Yeah.
All right, any other questions? Any online? Oh, I see a hand in the room.
How do I look online?
Okay.
All right, great talk. One thing about solar cycle prediction, obviously this is the root of the solar cycle, is that there's 10s, 30, 40, 50 published predictions of the solar cycle. And one of my pet peeves about it is that they always treat it as there's no north-south asymmetry. So great job in finally pointing out the root of the solar cycle, there's north-south asymmetry. But I wondered if you didn't get into it just because it may not be there quite yet, but have you looked at what you have for 23 and what you have for 25 and see if sort of the northern and southern hemisphere are switching, as in peaking in different times, alternating?
Yeah, that's definitely something we're interested in. And we can't really look at it for solar cycle 25 yet because we only have 2 years worth of data. Solar cycle 24 was the only one we can get like a clear idea from because we have the whole solar cycle. We did look at, I mean, if we go back, well, sorry, I went back too far. Like we have the end of solar cycle 23, and we can kind of see here that they have the same behavior, although it's still, they looks as though the southern hemisphere is generally stronger. At least the shifts are a bit higher generally, but it does appear as though for the end of 23 that at least like this minimum happens kind of later than it does for the northern hemisphere. And so that's something that it would be interesting to look at with all of cycle 23 and compare. So that's a good point. Yeah.
All right, let's give another round of applause.
Okay. Can't to just put it in my belt loop?
No, it's like a pain in the butt.
Oh, I see. It's a latch.
Yeah, so just,
Cool.
or you can set that, you need to just don't walk.
Wait, I have an idea. This is the whole point of the pocket.
And then for this, as you see, they are sometimes it's funky to just hit that button or click on the plus. Okay.
Yeah. Lovely, lovely, lovely.
Good.
Yep. Cool. All right. Well, I'm Hugo Metis. I'm from Regis University, and I'm working with the High Altitude Observatory. And we're doing co-alignment of Skylab imagery for coronal mass ejection analysis. And I'm working with my lovely mentors, Alice Lisinski and Daniela Lakatush. So, already a problem. Fantastic. Okay, so we're working with Skylab data. And so Skylab was a space station launched by the United States in 1973. It ran with 3 crews over 24 weeks. And it was, it burned up in the atmosphere in early 1974. It contains the telescope mount that we were working with called the Apollo telescope mount, which had a HAO developed coronagraph. And so the data that we have is completely is curated by HAO, and it's a series of roughly 30,000 35 millimeter film images that are ranging in different polarized images and 3 to 27 second clears of the sun itself. And so this was our first chance to get regular coronal mass ejection data. Before this, there are some drawings and such, but we didn't have consistent regular data in such a large amount. So the issue was, though, that the images themselves are not co-aligned in a way that we can actually use very effectively for analyzing the data. And so there's several issues that we have to cover first that kind of get in the way of actually aligning these images. So, for example, during the digitizing process of taking this film and digitizing it, it had in the clean room, it's impossible to get rid of every speck of dust and every hair, especially when these little film rolls are like, they're very small. So there was dust and hair on these images, and they'll show up. We'll see them later. They're very obvious. And so the occulting disk, which I'll explain what that is what it covers the corona, the sun itself, so you can see the corona, because otherwise the light from the sun itself would be far too bright to actually see the corona. And so the pylon that actually holds up the occulting disk can move, and it gets in the way quite often, and it shifts around quite drastically in some cases. And so alongside this, the diode matrix that is on the film that accounts for a lot of the error, and it stores all this information on position and such. It cannot perfectly account for all issues in the images. It would be impossible. So, and I'll show you in more detail these issues. So here we have some images, 9-second clears from that coronagraph. And as you can see here, so here's our occulting disk, and on the center here is what is used for calibration of the images. And these are the pylons that hold up the disk. And so you can see here, these white little specks all over, those are the dust specks that get in the way, and they create a lot of noise. Next, of course, is now you can see these are two subsequent frames that we were analyzing, and you can see the pylon shifts 90 degrees. That makes it very, very frustrating to co-align the images because this shifts around so much. And you can also still see quite a few dust specks. And the pylon motion, generally you'd find that when the computer on board was running the chronograph, the pylons didn't shift, but the astronauts got a little excited when they saw these coronal mass ejections, and they'd shift the pylon around to see it better. And so you get these drastic shifts. And of course, the main thing that we're trying to correct itself is the roll in the images. So we have these two images here, and this is the subtraction of those two images. And basically what it is we're taking the two images, and one of them is the negative pixel values, and we're laying them, and basically this feathering you see is if my hands were the streamers, what we want is for them to align and it becomes a gray space, like out here. But when they're misaligned, you have these black and white stripes. So one really important thing to cover before we continue is what is used almost entirely, this formula, variance, super important for how we work with our data. It's the measurement of the spread between numbers in the data set. And it's a measure of degree of dispersion, the degree of dispersion around the sample's mean. It's super important, and I'll explain later. We use it a ton, and without understanding what it is, you can't get much further. So we looked at some solutions and exploring how we can align this data. And of course, the simple idea of just, okay, we can by hand run through these images, and our eyes are very good at picking up discrepancies in the images. So, we could do that, but there's even just the 9-second clears is some 1,800 images, and that would take a very long time to deal with. So making an automated shift system would be vastly superior for getting to this database. And so then we explored just detecting coronal signal, those streamers or CMEs, just finding where they are in the image, and making that, using that to align them. And then we had to explore some solutions with dealing with the pylons. Because of that shifting around, we couldn't use them as a basis for aligning the images. And then, of course, the variance, as mentioned, and using edge detection filtering was explored to see if we could get more precise alignments. So we'll start going through the process of how the code works. First things first, very basic part of this is, so the original image are those circular chronograph images, and that'd be very, very big pain to shift around. So what we do is we turn them into polar coordinates, into rectangular images, and then from there to avoid edge effects, and if a streamer was right on the edge of the image, we would be missing a chunk of it. It would be very hard to detect. So what we do is we double the image so we can get that full streamer and avoid edge effects. And so from here, we want to get rid of that dust. The dust is causes, because we are using variance to detect the streamers and other events, we have to have as minimal noise as possible, and those white dust specks cause quite a bit of variance. So what we do is you see these white specks all over the dust. They're highlighted by a IDL edge detection processing. And you see on the left there, the diagram, it shows what the edge dog is doing, and it turns edges bright white. So they're very easy to detect. And then we average them out into the background, and they're still visible, but they create far less noise. And so from here, we're able to move on to the next stage, which is now we have to find those pylons in both images. And what we do is we take a single strip of pixels in the middle of the image, and we just run the pixel values. And the lowest value is always going to be the pylon, because the light is blocking out light entirely. It's an opaque object. And so once we found it, it's stored in the data, and we're able to manipulate it from there. And this gives us the kind of the big deal of how this works, is relative pylon positioning. And basically what it's doing is we have a 30 pixel wide box, this box here. And what that is doing is it's on the reference frame. It skips along, and if it detects a streamer or a CME, it will stop, and it'll basically take the second image and slide it across from pylon to pylon. So yeah, you can see this is roughly where the scans are happening, and then it skips over the pylons and just goes from pylon to pylon to get as much data. And we can, so if there's any very large shifts, 90-degree shifts or larger, we still have a chance of detecting them. And it just, it slides right across. Generally, where it would start is this is saying this is where this particular shift is centered, and it would immediately shift the image so that it's aligned with this right pylon on the top and slide across. And then what it's doing is it's collecting the minimum variance to be stored in a histogram, which I'll show you later. So this process can fail. It sometimes is not defined enough, the edges. So what we have to do is we take 2 more scans. And so these aren't our data. These are just showing what each filter does. These are basically just different mathematical formulas for detecting edges and displaying them slightly differently. But it gives us, each one is subsequently more processing intensive. So we try to avoid using them, and that's why they're in the order they are. And so if it fails that first process of running through the image without any filtering, it'll go to Sobel filter. If it fails again, it'll go to edge dog. And if it fails, then it's just allocated into a separate file, and that it's failed the scan. We don't have the information we need. So from here, like I said, we store the data in a histogram. And so the histogram takes where each minimum shift value is. And the shift value is the amount of pixels the image needs to shift to be co-aligned. And so what it's doing is we're looking for this peak. And we have those the parts that are skipping over dead space is very important, because you can see in those far left graphs, those do not have the thing that detects the signal and skips empty space. And we get a lot more noise, and so we're a lot less sure if that's the correct co-alignment. And then if it, with the dust correction, it's less obvious with just a single histogram, but when you run it over a larger chunk of the database, it actually shows up just how many more images succeed with the first scan. Whereas, so it saves processing power. We don't have to scan through as many. But far left is without that signal detection that detects empty space, but it does have the dust correction, and then we correct as we go. And then with all the correction, we get this really beautiful peak where it's very certain what shift value we need. And from here, we change that pixel shift value to arc seconds. And so this is measured in half degrees. So 1800 arc seconds is how the resolution we're working with. And it's stored in 2 separate files. The successes are thrown in that left file there, and that's just what it looks like. It says the arc second value and whether it was flagged. And then this is what the file looks like if it fails. it'll save it. And if they're fixed during that filtering process, it'll also tell us that. And sometimes we have a few where the pylon is located right on the edge when we double the image, and that's separately labeled as a separate issue. But then from here, this database is, we send, my mentor Alice runs it through a separate algorithm to convert the Skylab data to the new adjusted imagery. And so here are some lovely examples. On the left is just a single still of the difference. You can see that that feathering is greatly reduced. And here on the right is a GIF of the 90 frames, 9,700 to around 10,200. And the orange lines are just to get you less distracted from the pylons, but you can see the pylon on the right side shifts around quite a bit, but the actual streamer stays quite well between these orange lines. But on the left, it begins to stray upwards. And so it's a lot harder to actually watch and see that CME go off. So it just creates a lot cleaner data. Now, of course, this wasn't a perfect process. And so we have some unresolved issues. The code ran through just the 9-second clears. That's fine. The images were taken in such a short order that we can just do the 9-second clears and correct the rest of the data. But we only got 86% return on corrected data. And of that, less than 1% can actually be directly attributed to the pylon positioning. The rest is various other factors that we aren't 100% sure on. And that remaining 13%, it has multiple reasons why it could have failed. A lot of them had a correct position, like the computer detected exactly where it needs to be. However, we had a thing that detects how certain we are of that. If it was less than 15% of the histogram data, then we don't assign the value because it might be wrong. And then, of course, under a higher resolution, we could have bumped the image resolution to a quarter of a degree or further. And that would have given us a better chance of detecting those edges, but the processing power necessary, it gets very slow very quickly. And of course, a big part of the images that did fail is that the pylons covered up the streamers or coronal mass ejections. And if we can't detect those CMEs, we can't adjust the images. So it's only roughly 200 something 9-second clears. So that's what a high school intern can do some summer, But so with that though, now we have the ability to use those FITS files for analyzing coronal mass ejections. And we can also create GIFs and MP4s, which are super useful for some projects, as mentioned down here. There's some researchers looking for comets in the Skylab data around the sun. And this solution can be recreated for other experiments or other data sets that need to be adjusted in a similar fashion. And I would like to acknowledge all these institutes and my lovely mentors.
All right, thank you. Any questions? I have to remember to look at both sides of the room. All right, any online? Then I have a question. So this technique, I know it's with Skylab data, but could you foresee doing either the same or a similar technique with other older observations or older data from different?
I mean, if there's an issue with alignment, I can foresee that with editing of the software, you could very easily change it over to other experiments. I had actually, with Rachel's project, I had briefly mentioned that because she had to align images by hand, that conceptually something similar could be done there. So I can see where this would apply to several other data sets and be useful for speeding up processes with alignment, especially with those larger databases.
Very cool. Any other questions? All right, awesome. Let's get Hugo another round of applause.
Yes. No, it's mine now.
Okay. All right, so we are now going to break for lunch. So people online, we will be shutting down the Zoom and the YouTube video. And so visit our website to get that link back up for the afternoon session. And we'll be starting again at 1:15 p.m. Mountain Time. Presenters and students in the room, please come back just slightly before then so we can get started right on time. And I figured I started my session of hosting with a bad joke, so I would end it with a bad joke. Did you guys hear about the satellites that got married? The wedding wasn't much, but the reception was incredible. All right, thank you. And we'll see you at 1:15.